Hello, in this video we're going to talk about electrolytes, reactions in solution, and precipitation reactions, which is really just another type of reaction in solution. So first, a reminder of what a solution is. A solution is a homogeneous mixture of two or more things. The solute is the substance present in a smaller amount, and the solvent is the substance present in a larger amount. So solvent has more letters than solute, if that helps you remember which one is which. And we use these words quite frequently in chemistry, so they're very good to know. Some other words that are useful to know. A saturated solution has the maximum quantity of solute that can be dissolved in that solution. And this depends on temperature, depends on the substances involved, both the solvent and the solute. But at some point there's a maximum solubility. And I just said solubility, that's the amount of solute that will dissolve in a certain solvent. So when you have a saturated solution, you have an amount of solute dissolved that's equal to the solubility of that solute. That sentence was probably a lot more complicated than it needed to be. Hopefully you can look at the words on the slide and it'll make more sense. Okay, so the concepts of molarity and dilution were given in a previous video earlier in the semester, but here's a very quick review. So the concentration is the amount of solute in a given amount of solution, and you can use many different units for concentration. In chemistry, one of our major units we use is molarity, which is moles of solute over liters of solution. If it helps, you can say molarity, moles over liters. This depends on total volume of the solution after you add the solutes. And this is something that's really important to know because we use this a lot and we assume that you know it stone cold awesome. So please remember this. Now when you're doing a dilution, the moles of solute is constant and you're just changing the amount of solvent. So you can set up this kind of equation that will relate the concentration before and after depending on the volume before and after. And we talked about this before. Now, there are many other concentration units, like I said just a minute ago. One of the most common concentration units is grams per liter, because it's so simple to define. You have grams, you have liter of solvent, and you mix them together, and it's really easy to prepare. Also, there's mass percents. So the percent of the solute over the solution times 100 is a mass percent. You can also have volume percents, which is a volume over a volume. You can have a mass over volume percents, which is mass over volume. It just depends on what you're looking at. And oftentimes people don't specify, and they just kind of try to get away with saying that, oh, well, if it's, 0.9 grams in 100 grams of solution, well, 100 grams of solution is about the same as 100 milliliters of solution, so it doesn't really matter whether it's a weight or a mass over volume percent. Personally, that's one of my pet peeves, but hey, people do it all the time. Okay, so occasionally you have to convert between concentration units. Say somebody gives a concentration in one unit, you need to use it in a different sense. How do you do that? So, some suggestions. If you have grams per liters and you're trying to go to molarity, moles over liters, you just keep the denominator liters the same and you just convert the grams to moles and you're there. That one's pretty easy and straightforward. Now, if you want to go from mass percent to molarity, this one's a harder thing to do. So the first step here is assume some convenient sample size that makes sense to you. Concentration is an intensive property. It doesn't depend on how much of the sample you have. So you can start with some sample size, use that to figure out your concentration, and that is applicable for any sample size of the solution. Then you convert the mass of the solute to moles, and then you can find the total mass of the solution, and then figure out what volume that occupies. Because remember, molarity is moles over total volume in liters, so you have to figure out what that total volume is, and usually you'll need a density to be able to do that. Okay, down on the bottom, we have our example. So we have an aqueous solution that's 10% ethanol by mass, and it gives you the density, which you're going to need. So then what is the molarity of this solution? How would you go about doing this problem? So first, assume some sample size. If you have a percent by mass, it's very easy to assume a 100-gram sample. And that means that you have 10 grams of ethanol in your sample. And the math that shows you this is 10% is the same as saying 0.100. You can turn the percent into the decimal form. Then you just multiply. You have a 100-gram sample, and you multiply that by the percentage as a decimal, and then that gives you 10.0 grams. Another way to say this is that if you have your 100-gram sample and you're multiplying by 10% ethanol, which would mean 10 grams of ethanol and 100 grams of solution, then that gives you the same thing, 10.0 grams of ethanol. We did this in the empirical formula problems, assumed a 100-gram sample so that we could very easily convert from percentages to grams. So we're going to do the same thing here. Okay, now that we know we have 10 grams of ethanol, we can convert the ethanol itself to moles. This is our solute. Then we can do the same thing for the overall sample that contains both solute and solvent. So if we use the 100-gram mass and we use the density, which converts the mass of the overall sample into volume, so then this gives us our volume of sample in milliliters, and then we can convert that to liters, and we can find that 100 grams of this solution is about 101 milliliters, 0.1016 liters. Now we want to find molarity. We're in the home stretch. You just take moles and divide by liters, and you get molarity. So a 10% by mass solution of ethanol is 2.14 molar ethanol. So ultimately, when you're doing these kind of conversion problems, you really have to think deeply about what concentration units mean and how you can work to convert between them. All right, one thing I want to note is what we use m for. And the short answer is a lot. So a lowercase m is typically the unit of meters. Sometimes m will also mean mass when it's in the lowercase as a variable. Kinetic energy is 1/2 mv squared. That's mass as a variable. When you have it as a unit name, lowercase m, that's meters. Now, if you have it lowercase m and it's italic, that's molality, which is a new concentration unit that we introduce in the second semester of this course, so you don't need to know it now, but you'll see it at some point, so I put it here to be complete. When you're writing moles, please use MOL to abbreviate moles, so you don't get it confused with either of the M's. Now, when you have a capital M, that is molarity, and that's equal to moles over liters. It's a compound unit. And then finally, this here is molar mass, and I'm using a funky font to try to demonstrate that if you have somebody make a really kind of script M type of thing, that they're usually implying that they're talking about molar mass. It's really hard to represent on a screen. And I don't typically use this as a variable, personally, just because I think it gets kind of confusing. But you'll see people do that, make a really big script M, and use that to refer to molar mass. Okay, so the next thing in our video is we're going to talk about electrolytes. And I feel like we've said this now a couple times, once in Chapter 6, once in Chapter 10, but we keep refining the picture each time we talk about it. So now we're going to define strong and weak electrolytes. Okay, so a strong electrolyte, it dissociates completely. And so that means if you have sodium chloride, you're going to have sodium ions and chloride ions when you dissolve this in water. On the other hand, weak electrolytes are not completely dissociated. So if you have acetic acid here, it will dissociate into the acetate anion and the H+ cation, but it only does so a small amount. A couple percent will actually dissociate, and then the rest of it will stay bound together like it was a molecule. And so we'll write these double-headed arrows to show that this is also a dynamic process. So you'll have acetic acid dissociating into its constituent parts at the same time as you have its constituent parts combining to form acetic acid. And this goes on dynamically. It reaches some equilibrium value so that even though the individual atoms are going back and forth from these two forms, the overall concentrations are constant. And we do a lot of work on equilibria in the second semester of this course. Okay, molecular compounds don't dissociate, and therefore they're non-electrolytes. They will not conduct electricity across a solution. They don't make charged ions in solution. That's what molecular compounds do, which we've already talked about. So the thing new in this chapter is classifying solutes into these categories: strong electrolyte, weak electrolyte, and non-electrolyte. So here's a picture from a different textbook that talks about this. And then here's my slide on how to predict if a substance is an electrolyte. So you kind of work through these steps and identify what's what. Okay, so 6 acids are strong electrolytes. And I mentioned this in the video about acids in chapter 10. And at the time I said you don't need to know this. But now is the time to know it. So these 6 acids, please memorize them, are strong electrolytes. And basically, it's the halogens, chlorine, bromine, and iodine, with the conspicuous absence of fluorine. So hydrofluoric acid is not a strong electrolyte. It's a weak electrolyte. HCl, HBr, HI, the other halogens, when you form a binary acid with them, they are strong electrolytes. And then we'll use the word strong acid to describe this. Also, our very commonly used laboratory acids, nitric acid and sulfuric acid, are strong acids. And you don't quite have the context for this, but nitric and sulfuric acids are very commonly used in the laboratory. And then the last one on this list that we teach you in this class is perchloric acid. And this isn't very commonly used in the laboratory because it tends to form explosive mixtures. Not a good thing. But it is a strong acid. So, if an acid's not on this list, then assume it's a weak electrolyte, and that's a fairly good assumption. The list above is not a complete list, but it's good enough for the purposes of general chemistry. So those are strong acids. Now, strong bases are the soluble hydroxides. And this is really a subset of the third idea here, is that if a salt is soluble in water, it's a strong electrolyte. If your salt happens to be a hydroxide salt, then that makes it a base, because bases form OH in solution, and so, thus, a hydroxide salt that dissociates when it dissolves is a base. Now, most other bases are weak electrolytes, and these are generally ones that are derived from ammonia, or ammonium. Right? Ammonia being a base, it then forms the ammonium counterion as it produces hydroxide. So this is a weak base, and anything derived from NH2, NH3 is a weak base. Okay, again, if your salt is soluble in water, it's a strong electrolyte, because that's how ionic compounds dissolve in water. But there's one specific exception, is that halides and cyanides of heavy metals are often weak electrolytes. So mercury 2 chloride, lead 2 cyanide, these are weak electrolytes. Now, most organic compounds, and you'll see these because the formula is just CHO and N, they're non-electrolytes. The exception here is organic acids, which are usually weak electrolytes. Okay, and then the last concept in this video is solution stoichiometry. And this is just an addition to the concepts of stoichiometry that we talked about before, where a molarity to moles step replaces this grams to moles conversion we did before. Now, this is important to know because oftentimes we conduct reactions in solution, so being able to do stoichiometry around the reactions in solution is a very important thing to do. So again, when we talked stoichiometry in the first place, one of our initial steps in most problems was converting grams to moles, but now we're replacing that by converting molarity to moles. So what we're doing now is if you take molarity, moles over liters, and you multiply it by the volume in liters, then your liters will cancel, and then you're left with just moles of solute. And that's super easy to do experimentally in the lab, and it's pretty easy to do on paper too. So, molarity times volume gives you moles. As long as the volume's in liters, you're set. And again, that's analogous to our step that we did with stoichiometry earlier, where you take grams and divide by the molar mass to get moles. So you use these steps in the same way depending on whether you're starting in a solution or you have a solid that you're weighing out. So this is probably best described by an example. First, before we do stoichiometry, we need to figure out what the chemical equation is, for our end goal of calculating the mass of precipitate formed when we do the reaction with this amount of starting material. So we start by writing the reactants, and then we swap partners and make products. So barium and sulfate come together to make barium sulfate. The sodium and the hydroxide come together to make sodium hydroxide. And you have two sodium hydroxides because in each of the compounds that are reactants, you had two of either sodium or hydroxide. Now you got to look at the solubility rules to see how this works. And so barium sulfate is insoluble. It's listed as in addition to rule number 6. And then sodium hydroxide is soluble because alkali metal salts are always soluble. Okay, so we're making barium sulfate solid. Great, now let's move on to the next step. And here the balanced equation is rewritten. So we need to take our starting components, the 2.27 liters of 0.0820 molar barium hydroxide, and we need to find how many moles of barium hydroxide we start with. So again, this is the step that's analogous to taking grams and converting it to moles before you use the mole ratio from the equation. So here we take the volume of the solution, multiply it by the concentration, make sure that our liters cancel, and we're left with number of moles of barium hydroxide in the starting material. Now the stoichiometry step looks something like this. The moles of barium hydroxide that we found in the previous step is then multiplied by the mole ratio from the equation. So we have 1 mole of barium hydroxide, and that forms 1 mole of barium sulfate. So that's the mole ratio right here. Now we have moles of barium sulfate. Then it's good to go back up and check what the question is asking for. The question wants to know the mass of precipitate that's formed. So to find the mass, you have to use the molar mass here for barium sulfate, your product. And when you do that, you get 43.4 grams of barium sulfate as your answer. So again, the key piece of stoichiometry is this here in the middle. And then everything before and after that is just however you're going to get into moles on the left side and however you're going to get out of moles on the right side. Now let's make this trickier. So the text that's in black here is the same as the previous problem, but now we're turning this into a different problem by mixing a certain amount of the other reactant. And so the balanced equation is still the same, although now it's presented in a colored box. So now, since we have stated amounts of both of our reactants, we have to do a limiting reagent problem. Okay, so our process for limiting reagent problems is that we will convert both of our reactants to a product. And which product do you choose? Well, since the question is asking for the mass of precipitate formed, and we know that the barium sulfate makes the precipitate, it makes sense to convert both of these to barium sulfate because we're going to need that number anyways. This would work if you converted it to sodium hydroxide and then did a second step of taking your limiting reagent and converting it to barium sulfate, but that's extra work. So now we find the moles of each starting material, just like we did on the last slide, and so the first bit of this is just copied from the previous slide. And now we take the amount of sodium sulfate and do the same thing. Now we do the stoichiometry piece. So let me scoot this up. And the product from barium hydroxide, well, this is just exactly what we had on the last slide. So I don't need to talk about it. I'll just repost it here. And now with the sodium sulfate, you do the same process. You take the amount of sodium sulfate that you calculated by taking the volume and multiplying by the molarity. You use the mole ratio between the sodium sulfate up here and the barium sulfate. But, you have a 1-to-1 mole ratio up there. And then, well, since we previously converted this to grams before, I'm just going to convert it to grams again so we can compare in grams between these two. You could also compare in moles before you multiply by the molar mass if you would like. That's totally fine too. All right, so we have these amounts of different products. And then what's the key to a limiting reagent? That key is that the smallest amount of product is your theoretical yield. And the theoretical yield comes from your limiting reactant. So then to go back to answer our question, how much precipitate is formed when you mix these two together, it's still 43.4 grams of barium sulfate that's formed. You can't form 47 grams because you don't have enough barium hydroxide to pull that off. Now let's take this another step. Okay, in the last problem, the barium hydroxide was the limiting reagent, and we had excess sodium sulfate. Well, say you wanted to put an exact ratio of these two compounds together so that you didn't waste any of it. This is called a stoichiometric ratio in chemistry, and so say you wanted to run a reaction like that. Well, if you have that amount of barium hydroxide from the last problem, and remember that that was 0.1861 moles of barium hydroxide, now you can take the moles of one reactant, barium hydroxide, and convert it to the moles of the other reactant, in this case, sodium sulfate. So here's our mole ratio, and that's going from here to here, right? Going from one reactant to another reactant, which is totally legitimate to do. Now that we have moles of the other reactant, we can use the concentration of the other reactant to figure out how many liters of it you need. So there's a couple different ways to do this. The way that I like to do it is just use moles over liters, except put the moles in the denominator down here, so that then you cancel out moles of sodium sulfate, and you're left with just 1 liter on the top, and then your answer will come out to be liters because the moles cancel over here on the left. And remember, we're trying to calculate the volume of this sodium sulfate with this concentration required to completely react the barium hydroxide. Another way you can do this is just by using the equation m equals moles over liters, and then you're trying to solve for liters, and you know molarity, so you could say 0.0664 molar is equal to 0.1861 moles over liters, and just solve for liters. And this number of moles is this answer, right? The moles of sodium sulfate that you get after taking the moles of barium hydroxide through the mole ratio here. In this case, it's 1-to-1, so the numbers are the same, but don't always count on it being 1-to-1. So that's our process. You can solve for liters. So you could do it this way as well. I see a number of students do that. Maybe it works better for them. Totally fine. So back to this handout that I first showed when doing stoichiometry, is we're kind of back to the same plan of thinking about how the moles of one compound and the moles of the other compound are related by their mole ratio. That's the center of stoichiometry. What we're doing now is we're going from the concentration of a given solution using molarity to figure out moles of the given solute. And then we use the mole ratio to go to the moles of the other component we're trying to find. And then it depends on what the question's asking. These questions mostly asked what mass of product would you form, because it was mass of a precipitate. So then we use the molar mass to come back out. You could conceivably come out and have some question that wants to know concentrations when you're done. And so you could use molarity again that way, so on and so forth. So that's all I have for now, and thank you for watching.